Hello, today we're going to talk about reactivity 3.2.15 and 3.2.16. These are HL only topics, and it has to do with the electrolysis of aqueous solutions and then electroplating. So electrolysis happens in an electrolytic cell, so it's non-spontaneous. There must be some kind of energy source applied to make it happen. We've talked about the electrolysis of molten salts, which are fairly straightforward. You're putting energy in typically to split the salt and make the metal gain an electron or make the nonmetal lose electrons. In this case, when it's in an aqueous solution, there are multiple options available, and that's because you have water. And water can undergo electrolysis. So the water that's present in your aqueous solution can gain electrons to form hydroxide ions and hydrogen gas, or the water can lose electrons to become hydrogen ions, oxygen gas. So water basically can do both. And so that means at your anode, the anion from your dissolved salt can be oxidized, or water can be oxidized. And at the cathode, your metal ion can be reduced, or water can be reduced. So you're going to have to look and see which one is preferred in a particular situation to be able to determine the actual reactions that are happening at the anode or the cathode. So there are a few different things that you'll need to look at when deciding whether to oxidize or reduce the metal, non-metal ions or water in any given situation. And one of those things is the standard reduction potential, using your section 19 in your data booklet. You could also consider the concentration of the ions in your solution. This is an aqueous solution. You also want to consider the nature of the electrodes. So whether you have inert electrodes or reactive electrodes, or that's going to behave differently. So first, let's just look at the hydrolysis of water. Okay, so you can just apply a power source to water itself. Typically, I'll use something like platinum electrodes, but I've used like paper clips before to get this to work. You just need something that is going to conduct the electricity, and so you'll need some kind of electrolyte added. I will typically use something like potassium nitrate, but just enough so that the electricity can actually pass through the water. Anyway, so the reactions that are happening at the anode, you have the water being split into oxygen gas, hydrogen ions, and electrons. And so you're creating an acidic solution at the anode. And you can even use pH indicators to determine which one is the anode and the cathode. Whichever one turns acidic is going to be your anode. And then at your cathode, you will form hydrogen ions. You'll take hydrogen ions from the water and reduce them to hydrogen gas. So this is a net ionic version of the equation. And so over time, you're getting less acidic because you're removing the hydrogen ions from the solution. And so effectively with your pH indicator, this side will be a base. Now, if I wanted to get these two to add up properly, I would need to multiply this reaction by 2. So I would have 4 hydrogen ions with 4 electrons at the cathode, forming 2 hydrogen gas. And then you could add them together to get your overall reaction, But I do want to point out that you're producing these two gases, oxygen gas and hydrogen gas, and you are producing the gases in a 1:2 ratio. So you're always going to make twice as much hydrogen gas as oxygen gas when you're splitting water. Okay, so now let's say we have a concentrated aqueous sodium chloride solution. And let's first consider the cathode. So at the cathode, we could do one of two things. The sodium ions could gain electrons to form solid sodium. That cell potential for that reaction, the reduction reaction, is negative 2.71. Or we could take the water and form hydrogen gas and two hydroxides. Remember that on the last slide, that was a net ionic equation where I had the hydrogen ions from these two water molecules gaining electrons. Now, so these are two options. The cell potential for the water is negative 0.83. Okay. And so when we're doing this, look at your values for your reduction potentials. And these are standard reduction potentials. The water is much more favorable to gain the electrons, like significantly more favorable, because it has a much more positive reduction potential. So at the cathode, it's going to be preferred that hydrogen gas is produced and the water is being split. So this is our half reaction. At the anode, we have two options, the chlorine, and I'm going to write them here. I'm going to go ahead and write them as reduction reactions because that's how they're given in your data booklet. So that way you have an idea. We have that. But remember, at the anode, it would be the reverse thing happening. So my reduction potential for the chlorine is positive 1.36. My reduction potential for the water here is positive 1.23. And so you need to consider that how close in reduction potential these are. So it's a little harder to discern just from reduction potential. Based off of the fact when this reaction occurs as an oxidation, so two chlorides go to Cl2 plus two electrons, you're forming this chlorine, which is a gas, which can leave the solution. This is a relatively more favorable reaction when you have concentrated solutions because it's forming that relatively stable chlorine gas. However, if your solution is very weak or dilute, then the water is going to be preferred. So in dilute solutions, you'll have the water being oxidized to the 4 hydrogen ions, oxygen gas, and 4 electrons. So just kind of keep that in mind. Concentrated solution is going to favor the chloride ions, whereas in dilute solutions of sodium chloride, it will favor the water. Now let's talk about an aqueous solution of copper 2 sulfate with inert electrodes. So at the cathode, we have those copper ions that are gaining electrons to form solid copper. The cell potential for that is, the reduction potential is positive 0.34. For the other option at the cathode would be taking the water to gain electrons to form hydrogen gas and hydroxide ions. And the reduction potential for this one is negative 0.83. So the copper is significantly more favored. Okay. It's a little bit more complicated for the sulfate. So we're going to use our sulfate ion with 4 hydrogen ions. And again, I'm going to write these as reductions for our anode. just so you have an idea of what it looks like in your data booklet. So the reduction potential for this is positive 0.17 volts. But for the water, my reduction potential is positive 1.23. But consider that those are reduction potentials. So that means if these reactions were to flip, the oxidation potential would be negative 0.17, and the oxidation potential for the water would be negative 1.23. So the one that's more favored for our electrolytic cell is going to be the water. Because when you add that to your reduction potential here, it gives us a negative value, which is what we are expecting to find when it is a non-spontaneous reaction. Now, this only happens when you have inert electrodes, so like platinum electrodes or graphite electrodes, something that's not going to react. However, we can also do electrolysis of aqueous copper 2 sulfate solution with copper electrodes instead of inert electrodes. At the cathode, the same exact thing is going to happen. We're going to take those copper 2+ ions, they will be reduced to form solid copper with a reduction potential of 0.34. So this one is preferable over the water. At the anode, not only do we have the sulfate ion and the water, we also have a third option now because copper is reactive. The copper electrode itself can participate in the reaction. So that solid copper electrode can be oxidized to form copper 2+ ions and 2 electrons. And so this is going to happen because copper is more reactive than the water or the sulfate ions. And so you are in an interesting situation here where copper is being both oxidized and reduced, which is a kind of a cool process. So this is something that is called electrorefining, where you can take an impure source of copper and purify it through electrolysis using copper electrodes. It's pretty neat. Now we can also use electrolytic cells to do electroplating. So remember, electrolytic cells typically occur in a single chamber, and you're going to have some kind of source of metal source. This is going to be connected to your power source, and it's going to be connected to the anode. And so electrons are going to travel from the source of metal towards the power source, and then it's going to connect over to the object that's going to be plated. And so the electrons are going to travel this way. This is the cathode, and this is our negative electrode. You're going to need it to be in some kind of electrolyte solution, typically containing ions of the same metal, to simplify the process effectively. Now, there are a lot of different reasons why this would happen, but cathode is where reduction is happening. Remember that. So your metal ions will be able to gain electrons to form solid metal. And so it's going to form a layer of solid metal on the outside of the object, wherever it's submerged. So this could be for decorative reasons. You could be plating something like gold. Gold plating is very common. You could be plating something to control rust or control corrosion. So things like galvanizing. You could also be creating a sacrificial layer. So like coating something in a layer of copper, and the copper is going to oxidize and form copper 2 oxide or copper oxide. And it's just going to stay as copper 2 oxide. But it protects whatever's underneath it, whatever metal's underneath it. You could also plate it with things like chromium, which is going to give it enhanced properties. So there are a lot of different reasons you might want to plate a metal with a different type of metal. I would like to connect this very briefly with stoichiometry. So you might be asked about the mass of a metal deposited. So we can apply a certain amount of current over a certain amount of time, and we typically measure that in terms of amps. And amps is coulombs per second. The equation really is I equals Q over T. That's a G. I equals Q over T. Now this equation is no longer given in your data booklet. So I find it unlikely that this question, the questions related to this would have you use I equals Q over T. However, I do think it's possible that because you have Faraday's constant, that you might be given an amount of charge and have to figure out how much metal is plated based on that amount of charge. And Faraday's is a coulombs per moles of electron, and the number is 96,500. And so that's given in your constants list in your data booklet. So if I have, let's say I'm taking copper, I want to plate something with copper. This is a 2-electron process. I have some number of coulombs that I am applying to the solution, some amount of charge. I can use Faraday's constant. That's coulombs for every mole of electrons. For this process, there are 2 electrons for every 1 solid copper that's being formed. Coulombs cancel. Then I can use copper's molar mass, which is 63.5, to convert into grams of copper, some number of grams of copper. So I do think this type of question is fair game. However, the calculation with amps is probably not going to be on there. Okay, so we need to figure out the products formed during the electrolysis of a concentrated solution of potassium fluoride. I like to start with the cathode. So we've got 2 options, the potassium ions going to solid potassium, or we could take the water forming hydrogen gas. Now, if you looked at only the reduction potentials, you would maybe assume that the potassium would be formed, but solid potassium reacts very violently with water, so that's something to consider, that it's most likely not going to be the reaction that is favored. This is going to be the reaction that's favored with hydrogen gas and hydroxide ions being formed. Now, at our anode, again, we have 2 options. We have the fluoride ions forming fluorine gas and water forming hydrogen ions, oxygen gas, like this. Okay, so again, we need to think about reactivity. The fluorine gas is very reactive, and fluorine is extremely electronegative. It is much more likely to gain electrons than oxygen is. So I'm thinking about the reverse reactions when I'm thinking through this. The fluorine is much more likely to undergo the reverse and exist as fluoride ions. So that means this reaction is favored at our anode. So this is the equation at the anode, because the fluorine is less likely to exist as fluorine gas compared to fluoride ions. And so then the other products are the hydrogen ions and oxygen gas. And for this reaction, we have a metal spoon being plated with silver using an aqueous solution of silver nitrate and an impure silver anode. So I'm going to draw a very quick mock-up of this electrochemical cell. Let's see if I can draw a spoon. There's my spoon. Okay. And then it's in an aqueous solution of silver nitrate. And so the spoon is what's being plated. The silver is at the anode. The spoon is at the cathode. And when you're applying the electrical energy, the electrons are going to transfer from the anode to the cathode. When it does that, the silver ions that are in the solution are going to gain electrons and form solid silver metal on the surface of the spoon. So the anode, the impure silver anode, is going to decrease in mass over time, whereas the spoon will increase in mass because it's getting the silver plated onto it. You'll also notice, because aqueous silver nitrate has almost a silvery color to it. It's mild, but you will see it get more clear because the silver is leaving the solution. And you'll also see the spoon looking more silver as it gets plated over time. Okay, so using an electrolytic cell for electroplating is one of the scientific tools that you need to know for chemistry. I would spend some time, if you are able to get the materials to perform electroplating, please take the time to do so, because it's definitely going to be worth it. It's also just a cool experiment. If not, there are some really cool videos out there showing electroplating in action. So it's definitely worth your time to understand the process, know how it would be set up, be able to draw the diagram, and if you have the opportunity to give it a try, it's definitely worth it.